Swayam Prabha. Digital India. Educated India.
Here is the reaction of naphthalene with acetyl chloride in the presence of aluminum chloride, and it actually gives you greater than 90% of this compound. So if you look at the regioselectivity of this reaction, actually there are two possible products. So this is one, and the other one is actually the two substituted compound, which is as shown here, C double bond O CH3. Okay, so this would be position number 1, and this is actually position number 2, right? So this compound, this is a minor product over here. Okay, so the question that is really asked here is, how do we explain this? Okay, so the way we would explain this is, let's look at the intermediate that is produced upon reaction with naphthalene. So if I draw out naphthalene like this, okay, and we know that the reaction happens with the icellium ion as shown here. So the attack happens at this carbon, and then there's a movement of electrons, and so the resulting product that is formed is actually the one as shown here, right? So you have the H here, and you have C double bond O CH3, right? And that's hooked up to this carbon over here, and then there is a positive charge that develops here, and there is a double bond. Okay, so if I look at this system, I can see that there is delocalization across this allylic carbocation. Okay, now if I were to do the same reaction on the other position, I'm just going to draw out the structure over here, and you will understand the difference in stability. Okay, so here is the second structure as shown here, and there's a carbocation over here, and then there is the olefin over here. Okay, so as you can see here, there is little or no possibility of delocalization with this double bond. Okay, so there's an isolated double bond pretty much. Okay, so any delocalization that happens will involve this benzene ring. Okay, so once this benzene ring moves here, of course we can draw out resonance forms where there is going to be some level of delocalization over here, but this involves the loss of aromaticity. Okay, and therefore any structure that is going to be significantly different in stability will not contribute much to the resonance form, and therefore the stability difference between these two is quite large. Okay, so this compound over here, this intermediate over here, is more stable, and what we know from electrophilic aromatic substitution is that the stability of the intermediate contributes to the formation of or to the transition state that leads to its formation, and that becomes more stable, and therefore the rate of reaction goes up. So this helps us explain why this compound is the major product. So the next problem is understanding the reactivity of a heterocyclic compound, and this heterocyclic compound is called as furan, and furan is a very important heterocyclic compound that is used in the synthetic intermediate in many reactions, including to make pharmaceutically active compounds or drug-like molecules. So looking at this compound, this molecule is aromatic, as we all know. Now when you react this with acetic anhydride and BF3, you end up with essentially a compound that is substituted at the 2 position. So let's get that nomenclature first straightened out. So this is 1, 2, 3, and 4 and 5 are the same as 3 and 2. So these are the 3 positions that are important. And so if you see the Friedel-Crafts acylation reaction, that happens at position 2 rather than at position 3. Now, how do we understand this? So in order to understand this, let us first draw out furan and react this with the electrophile. So acetic anhydride, as all of you know, is basically CH3 C double bond O, O, C double bond O, CH3. Okay, so this is a compound that is precursor to the acylium ion. So your lone pair over here can react with the Lewis acid, and then it can come apart to give you the acylium carbocation. Okay, and so this is something that we could expect that will happen. And so you have O, C, CH3. This is the acylium carbocation or oxycarbonium ion that we're looking at. And so let's look at the situation 1, where the attack happens over here, and the bonded pair of electrons neutralizes the positive charge, and you end up with an oxygen here, and I'm just going to abbreviate this as E so that it's easier for us to draw the structure. So this whole oxocarbenium ion is going to be called as E plus, and then when it reacts you get E, and then there is a positive charge formed over here, and this double bond remains the way it is. Okay, so if you look at this structure, now I can draw a resonance form wherein we have this allylic, it's an allylic carbocation, so it can move in here and give you a resonance form which is going to look something like this. Oxygen is here, E and H remain in the same positions. This double bond moves here, and you get a positive charge here, right? So this is clearly possible, and now this is a very nice situation where you have lone pair on oxygen which can move in here, and it's going to give you a nice and stable oxocarbenium ion shown here, right? And so if I look at the structures, I end up with 3 of these structures, or resonance forms, 3 resonance forms for this, and subsequently it can lose a proton to give you the product. Now if we do the same chemistry on the other position, now if we see here the structure as shown here will first react with E plus, and it's going to give you a compound that looks like this. Okay, so keep in mind that this is 1, this is 2, and on the third position you have the electrophile attacking, and you end up with a positive charge here. Okay, so if we were to check this out, there can be a beautiful resonance form that can be produced here, and you end up with, again, a very fairly stable oxocarbenium ion as shown here. Okay, right? So this is also fairly stable. However, if you look at the number of resonance forms here, you have 2 resonance forms, right? And if you recall from the previous case, it actually had 3 resonance forms. And so therefore, having 3 resonance forms as shown here is going to be far more preferred when compared to the situation where you have 2 resonance forms. So which is how we can account for the high yield of this product and reduce selectivity. So isotope labeling is a powerful technique to understand reaction mechanisms. So shown below is an example of a reaction with C14 labeled chlorobenzene. So the question here is that does this observation support the formation of the benzene? Okay, so let's look at the question a little bit, in more detail. So here is chlorobenzene, and if you see here, this position is labeled with carbon 14. Okay, so it's a very convenient way to track the presence of, or where that carbon is, how that carbon continues to be connected in the product. So for example, if it was a direct substitution, if we replace chlorine with NH2, then this would be the exclusive product that is formed. But according to the observation, you have a 1:1 mixture, that is almost 1:1 mixture of the carbon 14 label being here versus being here, okay, which is right next to the NH2. So now how do we understand this, or how do we explain this observation? So if you go back and look at the mechanism of the benzene formation, so what we would expect is that the first step would involve the deprotonation of the carbon next to the chlorine, and so this is going to be pulled out, and once it's pulled out, you're going to get this carbanion, which is going to rearrange and give you the benzene. Okay, now if you keep track of the label starts at this position where it's on the carbon right next to the chlorine, and then subsequently it ends up with the benzene on the benzene. Okay, so I'm just going to redraw this here. So what we are suggesting is that the label is actually on this carbon. Okay, so now in the next step, which we are all quite familiar with, the amide attacks the benzene. So as you can see here, the incoming nucleophile can attack on either of the carbons of the triple bond. So in the red case, where NH2 minus attacks on the carbon with the label, then the amine ends up on the carbon, attached to the carbon with the label. But in the green case, where the amide can attack on the other carbon of benzene, so that is this carbon, then it is possible that the NH2 will end up on the carbon which does not have the C14 label. So as we know, this is the overall reaction is an elimination addition reaction, and since there is no particular preference for attack of one carbon over the other, what we see here is about a 50-50 mixture of the two products. That means both these attacks are equally likely, and therefore you see a 1:1 ratio of the products. So the carbon 14 labeling study therefore is very useful in deciphering the mechanism, and it suggests that the benzene could be a possible intermediate in this reaction. Suggest a synthetic scheme for the conversion of benzene to 1,3,5-tribromobenzene. So here is the reaction that we want to do. We want to convert benzene to 1,3,5. So if you number this 1, 2, 3, 4, 5 and 6, so you want to prepare 1,3,5 tribromobenzene. Okay, so let's now just look at a straightforward bromination to begin with. So if I start with benzene and I use bromine and aluminum bromide or FeBr3, then I get bromobenzene. And now under maybe heating conditions or under extreme conditions, let me do another bromination. And what's going to happen is, we know that bromine is orthopara directing. So at best, you might get 1,4-dibromo or maybe 1,2-dibromo benzene. So in this, using this methodology, we will not be able to get the 135 substituted benzene ring. So in order to get 135, one strategy that we could adopt is that if you could start with a substituted benzene compound, which we have to prepare from benzene itself, and then if that is actually orthopara directing and if it's highly activating, then it's possible that you can prepare 135 tribromo benzene. In this case, it will be 246. After you remove the X, you're going to get 135. Okay. So this numbering is just for our own convenience here. So if you remove X here, then you get 135 tribromobenzene. So therefore, this might actually be a better strategy for us to adopt if we want to convert benzene to 135 tribromobenzene. Now, we have looked at diazonium salts in our class, and diazonium salts are very good sort of substrates for us to prepare benzene. So if you prepare a diazonium salt and if you react it with H3PO2, the product that you get is benzene. So if we can somehow convert, so therefore this might be a good sort of protective group, or it can be a group X that can be used for conversion of X to hydrogen. Okay. So now how do we prepare diazonium salts? We prepare it from the amine. So the strategy that we can propose is that we start with aniline, or we can think about going from aniline. If you add bromine to aniline, we've already looked that in class that you get 135 or 246 tribromoaniline. And now if you're able to diazotize and produce the diazonium salt, which can then be reacted with H3PO2, then the product that you would get is 135 tribromobenzene, and of course the byproduct is nitrogen. Now how do we convert benzene to aniline? So the way we would do this is to take to do a nitration on benzene to get NO2 nitrobenzene, and then do a very simple reduction, which is a tin NaHCl reduction to get aniline. So to summarize, what the key step here is that if we convert aniline to diazonium salt, then the diazonium salt can actually be removed by adding H3PO2. So this becomes a very useful way to access various regiochemical outcomes in benzene rings. So if you, in some cases, you may want to get the meta product, or some cases you want to get the orthopara product, etc. So those can be sort of achieved by manipulating the kind of group that is being involved. To summarize the various reactions that diazonium salts can undergo, so if you start with benzene diazonium salt as shown here, if you react it with CuBr, then you get bromobenzene and nitrogen. Similarly, if you react it with copper chloride, then you get the chlorobenzene salt. And similarly with iodide. Now, if you react this with copper cyanide, you can actually form a carbon-carbon bond, which is very, very important in many reactions that we want to do. And so this becomes an excellent method for us to make a carbon-carbon bond. You can also convert it to the fluoride by reacting it with HBF4, which is basically BF4 minus and H plus, and that's going to give you BF3 and nitrogen as byproducts. You can also convert a diazonium salt to phenol by reacting it with aqueous acid. And just now we discussed this, you can react a diazonium salt with H3PO2, and that nitrogen is replaced by a hydrogen. And another method to produce phenol is to react it with Cu2O in the presence of copper nitrate. Okay, so this is the kind of variety of reactions that diazonium salts can carry out, and this becomes very useful in many of our organic synthetic procedures. Suggest a method to produce an azo compound from aniline. So the way we would want to, first of all, let's look at what an azo compound is. So an azo compound is basically a nitrogen double bonded with nitrogen with two alkyl or aryl groups flanking it. So one of the methods by which you can produce azo linkage is to use diazonium salts. So if we react phenol with this meta-bromo benzene diazonium chloride, then the product that you get is a diazo compound with, this is the kind of diazo compound that you get. So clearly the nitrogen, triple bond nitrogen here is involved in the reaction, not in the way that we are used to, but in a very different way. So this kind of reaction also works well with basically with electron donating groups or electron rich benzene rings such as phenol and dimethyl and so on. So if you look at the mechanism with dimethyl so what in essence happens is that your lone pair on the nitrogen can sort of move into the benzene ring, and the benzene ring electrons can attack the diazonium salt. So once this attack happens, then you get this diazo compound, and then loss of the proton on the benzene ring is going to give you N-dimethyl aminobenzene. Okay, so these diazo compounds are actually highly colored, and they become a very useful way for us to prepare dyes. So a lot of dyes have diazo compounds. Predict the products of the following reaction. In what ratio will they be formed? So here is another example of labeling experiment. So we start with this chlorobenzene, which is C14 labeled, and react it with sodium hydroxide water at 395 degrees centigrade. So to put this temperature in context, the boiling point of water is 100 degrees centigrade, and we are clearly maintaining a temperature which is extraordinarily high, and so therefore these are extreme conditions. So we've already discussed this. Under extreme conditions, it is possible that nucleophilic aromatic substitution or benzene kind of mechanism is possible. So here this is not a substrate for nucleophilic aromatic substitution, so therefore you can expect that a benzene type mechanism would occur. So again, keeping track of the carbon label, hydroxide can attack at one of the ortho positions, produce this carbanion, which can then kick out chloride, and you get benzene. And as we discussed earlier, this benzene, there is no particular preference for attack or for reaction with one carbon or the other, and therefore you're going to you would expect to get a 1-to-1 ratio of the two products. So please keep track of the label when you're trying to solve these types of questions. So when you do the experiment, you get an almost 1-to-1 ratio, which is 54% of this product and 43% of the other product. Again, this is an example of using labeling to study the mechanism, and it helps us understand the mechanism better, and it also helps us to reason out what kind of intermediates are produced.